All right, so let's take a look at how we're going to analyze the data from your bomb calorimeter and your solution calorimeter. So I gave you, what we have here in this template is a sample data that you can get from the simulator. Okay, remember you did your simulation a couple of weeks ago. So you have your own standard run and unknown run. So this is my standard run and unknown run from that simulator. So I'm going to walk you through the analysis of the data. Okay, so let's see. Let me maximize this. Oops. This is an Excel template, or is this this is a Google Sheet. I have to download the Excel file. Open that file. Close that other one so I don't get confused. Oh, I already have the Excel template. Huh. And make sure you enable editing. Am I recording? Yeah, I am recording. All right. So, here's a screenshot of the simulation I did for benzoic acid, the standard run. Okay. The mass, what's the mass of my sample here? It's 0.9030 grams. So let's enter that. And the known delta U, let me adjust this, for the combustion of your sample on a per gram basis. So what you need to do is you're going to look at the bottle that has the benzoic acid. What's the value? Give it to me in megajoules per kilogram. 26.454. 26.454. Just pass it around. 26.4454. But that's megajoules per kilogram. So what would that be in kilojoules per gram?
Same.
No, joules per gram would be different. Always.
Okay, so let's see. It's a Q over sample.
Kilogram. This is negative.
What you said, negative.
Q sample is, what was it? 24.654.
26.454.
26.454. Aha. 26.454 megajoules per kilogram. So I want that in joules per gram. So 1 megajoule is 10 to the 6 joules, right? And a kilogram is 10 to the third grams. So basically, what do? I end up multiplying it by 10 to the third. So 26,454 joules per gram. That's the amount of heat generated by burning your benzoic acid sample per gram. So this is 26,000, what was it? 454 joules per gram. So that's actually delta U, okay? Remember, bomb calorimetry, Q of reaction at constant volume will give you delta U of the reaction. So that should be minus 26.454 joules per kilogram. So let me fix this one. There should be a minus here. All right, so what's the actual Q of the sample that was actually run? We did not use 1 gram, we used 0.903 grams. So what would be my formula here?
Multiply two cells together.
Okay, so whatever, adjust this so I can see the formulas better. Okay, so this is going to be equal to the value per gram times the actual number of grams, right? So that should be the Q, the actual Q of the sample. Now, the wire that was burned also generates heat. So how do we figure out the mass of the wire that was burned? You look at our data here. We have wire before is 0.0236 grams. The mass of the wire after is 0.0180 grams. So I can put that here. I can just say 0.236 minus 0.0180. That's how many grams, right? So 0.236, 0.0236 minus 0.0180. So that's the mass of my wire. Yes.
Also times 1,000 being in kilojoules.
Oh, correct. Divided by 1,000, right? This is joules. So you divide by 1,000. Just convert it to kilojoules. Because I want the answer there in kilojoules. Thank you. Bonus? All right. What's the known delta U for? What's the known delta U for the combustion of the wire? Again, it should be negative, and it's given in the what do you call this? Spool. The spool that had the wire. It's given to you in calories per gram. What is it?
You have.
1,400.
1403, 1400.
1,400.
Is it 1400? 1403?
It says 1,400.
Okay, 1400. So it should be negative. So minus 1400 calories per gram. But how do you convert calories to grams? I mean, calories to joules.
It's like 40,
It's another unit.
I forgot. Right.
1 joule is
It's like 4.1.
one thermochemical calorie is 4.184 joules. So I have to multiply this by 4.184 to get the value in joules per gram. Okay. So so this one, Q sample, what's our Q sample? We have to multiply this by our Q sample was minus 2454. I'm just gonna leave that there. I've already got it calculated on Excel anyway. Q for the wire is minus, what was it? 58, 57 point something. Well,
5857.6.
okay, so it's minus 1400 calories per gram times 4.184 thermochemical joules per thermochemical calorie. Okay, so that's Q for the wire on a per gram basis. Okay. So that's minus 5857.6 joules per gram. Now, if you're gonna use that later for your standard run, for your experiment, you're not gonna change that. It's the same standard that you're using for the wire and the benzoic acid. So what's the actual Q for the wire?
Apply that by the grams and then divide by 1,000.
Yes, so you multiply that by the mass of the wire that was burned, and then you divide by 1,000 to convert it to kilojoules. Notice that the bulk of the heat generated is coming from which one? The sample or the wire?
The sample.
The sample. It's 0.03 versus 23.88 kilojoules, right? So you can pretty much actually ignore the wire, but since you have information about the wire, you might as well put it in. Okay, so measure delta T from the graph. This is what you get from your thermogram, right? And let's just use the one that's shown here. So what's our final temperature? 26.272. So this is going to be equal to the final temperature, which is 26.272, minus the initial temperature here is 24.192. That's Kelvin.
Well, how did you get, B11 again?
This one right here, that's the mass of the wire that was burned times the delta U per gram for the burning of that wire. And then divided by 1,000 to convert it to kilojoules. Okay, measure delta T from the graph is 2.08. So how do you determine the calorimeter constant? The basic idea in calorimetry is Q of your reaction must be equal to minus C calorimeter times delta T, right? That's the amount of heat that would have to flow in or out to reverse temperature change that you cause. That's why there's a minus delta T there. So what's our Q reaction? This is Q sample plus Q wire, the actual Q sample and Q wire for your run equals minus C cal delta T. And the purpose of the standard run is you want to know what this C cal is. So how do I solve for C cal? Calorimeter constant.
The Q divided by,
The sum of the Q's, Q sample plus Q wire
divided by delta T.
divided by delta T, but there's a minus sign here. So that's going to be your formula. All right, so let's go ahead and do that. So this is going to be equal to minus open parenthesis Q sample, the actual Q sample, not the per gram sample, not the per gram value, plus the actual delta U for the wire, the actual Q for the wire. Okay, that would be in kilojoules, right? Divided by delta T, which is 2.08 Kelvin. That's kilojoules per Kelvin. All right. Now for your actual lab data, I've given you when I gave you a link in the assignment for submission of the report. I've given you a link to a Google sheet that has like 5 or 6 standard runs from the last 2 years, including yours. So what you'll have to do is you're gonna have to take the average of these runs, and then maybe you can put an average right here in the next row or something. So you just duplicate. You just basically you can just copy this formula and just enter the data from the different runs. All right. So that's how you calculate the calorimeter constant. Let me pause this or stop it.